Hello, I welcome you all in this presentation related with the subject failure analysis and prevention. In this subject so far we have talked about the fundamental sources of the failure and thereafter we started the general procedure of the failure analysis, and nowadays we are talking about the general procedure of the failure analysis wherein we have talked about various aspects, but in this presentation we will be describing on how to determine the type of fracture, determination of type of fracture. So, it is obvious that this one will be related to those cases where the suppression or the fracture of the component takes place during the failure. You know that we have talked about the NDT, non-destructive testing, which is used for determining the discontinuities, whether they are present at the surface or within the or inside the surface of the or underneath the surface or below the surface of the component. Destructive testing where the mechanical properties been evaluated in terms of hardness, toughness, tensile strength, then we have also talked about the macroscopic analysis, wherein the origin or initiation of the fracture, then direction of the crack growth, in under the macroscopy of the fracture surface, and thereafter we have also seen the microscopy of the fracture surface, wherein primarily we find the surface features like dimples, cleavage facets, intergranular fracture and fatigue fracture through striations. So, striations are the microscopic features on the fracture surface. Apart from that, under the metallurgy, which is a very important aspect related to the failure analysis, under this is used for determining the phase and the grain structure which is present in the failed component. So, basically in front of us now we will be putting the information related with all these things which have been completed for determining the type of fracture which has taken place. So, there can be a single crack or there can be multiple cracks identified through the NDT, or it can be the notch or any other form of stress razor. So, actually this information will be used to identify if it is the fatigue fracture or the tensile brittle fracture or ductile fracture, or the fatigue has taken place in the corrosive environment, or the fatigue has taken place in the dry conditions, means under the fatigue conditions. Similarly, the mechanical properties, it is of the high tensile strength or it is of the low tensile strength, similarly the high ductility and the toughness. So, accordingly the material behavior can be expected. If it is of high strength, low ductility, low toughness, then it will tend to fail in the brittle manner, and if it is of low yield strength, high ductility and the high toughness, then it will fail in ductile manner, provided it has experienced some other effects, it has been subjected to the special kind of the changes or unique changes during the service, whether it is high temperature or the low temperature, or the structural instability has occurred in the material. then the origin and the direction of the crack growth. So this is very important. We have to keep the macroscopy, microscopy and metallurgy also in mind. The kind of the fracture surface which has been created. If the fracture surface is flat or it is showing the shear fracture like this, or the fracture surface is showing the cup and cone kind of the fracture like this. So this will be indicating the will also be indicating the kind of the fracture it would be there. So macroscopy will show the general features present on the fracture surface in form of the extent of deformation which has taken place, the kind of stress conditions which were present, and whether it is the slant fracture or the flat fracture or the cup and cone kind of fracture. So all these things will be indicating the kind of the fracture which has taken place, primarily in terms of the brittle or the ductile fracture. Microscopy indicates the micro fracture mechanisms, microscopic fracture mechanisms, like the dimple fracture indicates the ductile fracture, cleavage facets indicates the brittle fracture, intergranular fracture also is a type of the brittle fracture, and the striations correspond to the fatigue fracture. So and thereafter the metallurgy. From the metallurgy we will be able to know that in a given material what are the different types of the phases, whether these phases are soft or they are hard, or there is a mixture of the hard and soft, or hard phases are present in the soft matrix, or vice versa. Similarly, the size and the shape of these the phases which are hard or the soft, and how are they distributed, means where they are present, that will also affect the way by which the cracks or the voids will nucleate and then subsequently they will grow. So information about the microstructural aspects and so means a phase structure and the grain structure combination, so phase structure or grain structure, all this information is used to determine the type of fracture in comprehensive manner. So we will be using the information gathered from all these steps in order to determine the type of the fracture which has taken place. Now we will elaborate that what will be the unique issues and what are the features which are used to interpret the type of the fracture which has taken place or which can be determined, which can be used to determine the type of the fracture in a given situation. So basically the grouping or the classification to determine the type of the fracture is not based on the kind of the deformation, macroscopic deformation which has taken place. It is the classification is not based on the deformation, because the simple the ductile fracture indicates a lot of deformation prior to the fracture, while the brittle fractures show limited deformation prior to the fracture. So this is one thing, but the microscopic fracture mechanisms are basically used to classify the type of fracture which has taken place, and for that what we have to keep in mind is that the presence of the dimples will suggest the formation of the voids, and their coalescence will indicate the ductile fracture, and which also indicates that material is fracture tough and it's the high energy fracture. It will take lot of load, means the load carrying capacity will be good. At the same time it will absorb, means the impact resistance will be good, and it will be it will show the good elongation. So the presence of the dimples, so this is one thing. Similarly, the presence of the cleavage facets onto the surface. I will show through the slides how to recognize and what interpretations can be made through the different microscopic features. So cleavage facets indicates, so this is basically the bright, the flat, bright microscopic surfaces which basically appear in form of the river patterns, or this is also called the fan shaped features on the surface. These indicates basically the transgranular fracture, which is basically a brittle fracture occurs with the limited deformation, but there can be other, in unique situation there can be lot of deformation, but finally the fracture occurs to the cleavage facets. So that will be classified as a brittle fracture. Then transgranular fracture, and it's considered as a low energy fracture, offering the low fracture toughness, limited fracture toughness, and the limited ductility in the material. Maybe yield strength may be high for such kind of the fracture conditions. So material show limited ductility, limited impact resistance, and maybe it has a high yield strength and the tensile strength of the material. Now we will talk about the possible the features which can be there, and what kind of interpretations can be made with regard to the microstructure of the material. Say in a metal system, in polycrystalline metallic materials, we may have just like this, we may have a single phase. So number of crystals of the same phase. So here no second phase particle. So in this case the material will show extensive ductility, because there is no second phase where from the voids can nucleate due to the differential change in the dimensions, and which can lead to the cracking. So when such kind of the systems we have, it elongates or it deforms, elongates significantly, so offers the high percentage elongation. It offers the good ductility, good toughness, but maybe the low strength of the material. But in case when it has number of the second phase particles, means here and there we have some hard particles located in the material, and in that case when the load, external load is applied, so these hard phase particles, these hard second phase particles, they do not deform by the same magnitude as the soft matrix. So because of the differential deformation, differential change in dimensions, one will be deforming more than other. This situation leads to the formation of the void. Void is formed at particle matrix interface. So if this is the particle and all around it has a matrix, then somewhere wherever the stress concentration is high, the gap is created. This is what happens. So, but the gap creation in case of the spherical fine particles become difficult as compared to the coarse and elongated particles. So, if the particle is of the needle type, in that case near the tips the stress concentration is high. So, the void formation between the particle and the matrix, means the second phase and the matrix, becomes easier. So, the voids are formed, and once the voids are formed at all these locations, then they will be growing, and consequently all these coalescence of all these voids will be taking place, and which in turn will be leading to the separation of the component under the effect of the external load. So, basically in this kind of the mechanism, voids first nucleate at the particle matrix interface, and then they grow, and after the growth their coalescence occurs. So, once the coalescence occurs, then it reduces the load resisting cross sectional area, and which eventually causes the fracture or the separation of the surface. This mechanism typically is known as dimples, wherein the fracture surface features wherever the particles are there, say in this matrix this is one particle, and here the voids are being nucleated under the effect of the external load. They will be growing, the voids will be growing like this around the particle, and these particles, when the fracture occurs, eventually due to the coalescence of these voids, what will be finding, number of the conical shaped of the different sizes and shapes, dimples. Dimples are the conical shaped features which are present on the fracture surface, and of course these particles, hard particles, will be present at the root of these dimples. So, their analysis can be performed to see the particles present at the root of these dimples can be performed to see what these are made of. So, there can be different situations under which the void nucleation takes place, and there are three types of situations where the dimple formation and their subsequent growth takes place. One is where the second phase particle and it is subjected to the external loading. So, one void is nucleated all around it, and in the second case, when the particle is of a needler shape or it is elongated, obviously the nucleation takes place in the area of high stress concentration. So, obviously in that case the locations where stress concentration at the tip of the second phase particle is high, the void nucleation takes place, and in the third case where the plane strain conditions exist, the void nucleation occurs in different way, which I will be showing in this diagram. So, now we will be going sequentially through the various aspects related with the fractures. So, what we will be seeing first, that the fracture broadly can be grouped in two ways. One is that the way by which crack grows during the fracture. So, there can be a situation where these are the different grains present, and if we have one crack here and it has to grow. So, irrespective of the phases and the boundaries, if it grows perpendicular to the direction of the external load, then in that case, so it does not follow any particular direction, but it grows perpendicular to the external loading and not along the particular direction, then and the crack grows across the grains, it does not follow the grain boundaries. So, that is the kind of this kind of fracture is known as the transgranular fracture, where the crack grows across the grains, not the grain boundaries. This is one thing, and in this situation mostly the crack grows perpendicular to the direction of the external loading. Then this kind of the fracture is mostly observed in the BCC metal systems like iron, chromium, tungsten, while in case of an HCP hexagonal closed packed metals like zinc, beryllium, magnesium, because these metals have the limited slip system. So, in these cases mostly the crack tends to grow in transgranular manner, while the FCC metals are immune to the transgranular fracture. This is the one way of talking about the fracture. And the second one, when we find that crack follows preferentially the direction of the crack growth follows a particular direction during its journey. So, like say here the crack is growing, so the crack will be growing along the grain boundary in this case like this. So, when the crack follows the grain boundaries of the particular metal, in that case we find that grain boundary of one grain, or then of another grain, and then of third grain. This is the kind of surface which we find at the grain boundary. So, this is one grain, this is second grain, and this is third grain. So, in the fracture surface basically we are able to see the grains. So, when the crack follows the grain boundaries, then we call intergranular fracture. Most of the time we find a mixed kind of fracture, mixed mode of fracture, where we can see the dimples, we can see the cleavage facets, we can also see the intergranular fracture due to pulling out of the certain hard faces. So, a combination of all these fractures is observed in the real fractures, and that is why they will look more complex. I will talk about one additional thing, like in a metal system where few hard particles are present here and there, and if the transgranular fracture is taking place. So, there are two possibilities. One is like say the crack may grow in transgranular manner here, and this is say completely soft matrix, and then through this one this is the soft matrix, and these are the particles which are hard and brittle. So, it is possible that the soft matrix may fail in the dimple, soft matrix may have the dimples on the fracture surface, while the hard and brittle particles where if their fracture takes place, so they will be showing the cleavage facets. So, we can see a combination of on the fracture surface there are certain zones where cleavage facets are present, and in the rest of the areas we have mainly dimples here and there, and here the cleavage facets at certain locations in localized manner. And if under the external stresses, instead of getting fractured, these particles they get pulled out. So, pulling out will be leaving some vacant spaces on the fracture surface. So, these areas may look dark, and so that will be the location where from these hard particles have been pulled out and they have not fractured. So, the metal systems having the hard and brittle carbide particles or the like silicon carbide in aluminum matrix, silicon particles, coarse polyhedral shape primary silicon particle in aluminum silicon matrix, all these will be fracturing either in the cleavage facets manner, or they will be getting pulled out under the influence of the external loading. So, what we can see in this diagram, classification is based on the microscopic mechanisms of the fracture and not the macro level deformation, like macro level changes which are taking place in form of the deformation. So, what it shows that this is the direction of the crack growth in case of the transgranular fracture, where the crack growth follows crack grows across the grains, means through the crack propagates through the grains and it does not follow any boundary or a particular direction, and this kind of fracture is known as transgranular. And this is the fracture where the crack has grown along the boundary of the grains, and that is why this type of the fracture is termed as intergranular fracture. Now, now how the crack grows during the during its growth. So, the crack propagation, based on the crack propagation, we can have the transgranular fracture, which is in form of the cleavage facets, or intergranular fracture may happen under the certain conditions, wherein like the poor phases are present in the metal, like there will be certain cases why the crack will grow preferentially along the certain grains. So, if the grain boundary is weak, then crack will prefer to grow along the grain boundary and it will lead to the intergranular fracture. There can be three situations for this kind of the fracture to occur. One is the metal system which is present at the grain boundary has the limited deformation capabilities. So, it is very brittle, limited deformation systems or limited deformation capabilities. The second is very poor phase or phases like carbides. In case of the iron carbon system, it is a cementite is present as a network in the steel. Since cementite offers very low strength and very high hardness, so it will tend to fail easily, and it also lowers the tensile strength of the steel. So, presence of the poor phases in form of the carbides, tungsten carbide or chromium carbide, especially at the grain boundary, this also weakens the grain boundary area and causes the intergranular fracture preferentially. And the third one, like some special elements are present primarily at the grain boundary. So, presence of specific elements at the grain boundary also leads to the weakness of the grain boundaries. For example, presence of oxygen in iron and the nickel alloys like inconel, this causes the intergranular fracture. Similarly, the antimony in case of the copper alloys causes the intergranular fracture. So, these are the three things: either the metal system present at the grain boundary has the limited deformation capability, the phases are very poor in terms of the load carrying capability and in terms of the ductility. So, they provide the easy site for the nucleation of the voids and subsequently their coalescence can lead to the intergranular fracture and the presence of a specific element. So, these will be leading to the embrittlement of the grain boundary area to cause the intergranular fracture. So, from here we can easily see these are the cleavage facets which are present and indicating the direction in which the crack has grown, while in this particular case where we can see the grain boundaries, we can see that individual grains, all these are the individual grains suggesting the intergranular fracture. So, steel can fail in transgranular way or the intergranular way if some undesirable phase precipitation or element precipitation has taken place at the grain boundary, then it will be leading to the intergranular fracture. So, this is also indicating that how the grain boundary, if the weak phases are present at the grain boundaries, then how the fracture will be facilitated. So, these are shown, these are the second phase particles. So, if these are all these are second phase particles present at the grain boundary under the influence of external loads. So, just ahead of the crack tip, what we can see, we can find the excessive deformation in this area. That deformation will be differential. Of course, the particle will not be deforming it the same way, in the same way as the matrix. So, more deformation of the matrix will be leading to the formation of voids. The void size will be larger here, here the voids will be formed here and here also of the reducing in size, and then the continuous growth will be leading to their coalescence and the separation. So, here the grain growth at the boundary is taking place, or in the direction it is taking place in such a way that wherever the particles are there, voids are formed, and subsequently their coalescence leads to the fracture. So, in all these cases, we will be finding the dimples both the sides. So, as I have said, ductile fracture primarily involves the dimple fracture, which is a high energy fracture, and the fracture of tough systems shows this kind of the fracture, while the brittle fracture shows the cleavage facets, and the intergranular fracture, which indicates the low energy fracture and found in brittle systems. So, this is the schematic way by which the crack grows. In the case of the transgranular fracture, the crack grows through the grains, but here the crack grows along the grain boundaries preferentially. Then we can say how the ductile fracture is observed in a typical tensile test of the material. This is what has been shown here. So, evolution of the failure in case of the evolution of ductile failure in case of the tensile test. So, under the influence of external loading, there will be deformation, there will be knacking. So, this knackings, when the knacking starts, we find that some of the voids are nucleated at the second phase particles, and subsequently their coalescence leads to the growth. So, the void growth and the linking leads to the reduction in cross sectional area, and then subsequently the shearing of the subsequently the fracture takes place. So, when we see such kind of the fractures, this kind of fracture typically shows the flat fracture at the center and the shear fracture at the near the surfaces. So, here if we see this one, the flat fracture, which is basically typical indicator of the ductile fracture, but here the flat fracture zone is being formed by the nucleation of the voids, and their subsequent growth is leading to this zone. And that is why it is important to understand the microscopic mechanism of the fracture. The central fracture surface is formed by the void formation and their growth, and what we can see at the root of these voids, some hard particles are present, some precipitates are present, which will be facilitating these the formation of these dimples. And these dimples, we can see here the large size dimples and fine size dimples, both kind of the dimples are present on the fracture surface. As I have said, these are the three ways of the void formation. This is the second phase particle, there is another second phase particle, and this is third second phase particle. So, when the second phase particle may be present in form of the inclusions, these may be in form of needles, or triaxial stress state exist. So, in that case, in all these three cases, how the void formation takes place. So, the second phase particle, when the inclusions are present and the material is deforming, then we will see the void is formed both the sides, and this eventually causes the formation of the dimples. But in case of the needle shaped constituents or needle shaped second phase particles, the voids are formed at the tip of the needles, so that so that void can be formed, and at these locations the stress concentration is high. When the triaxial stress state exists in this case, so in this case the void will be formed all around the second phase particles. So, these are the different situations where such kind of the void formation takes place. So, it may happen around the whole, so it is basically the whole or void formation often around the weakly bonded particle, This also can happen when the cracking of the particles takes place, growth of the pre-cracked particles, or cracking in a matrix of the limited ductility in which faceted particles causes the stress concentration. So, presence of such all these hard particles will be leading to the formation of the voids. One typical example here is how the voids are formed in the real system. This shows the two micrographs. In one case where manganese sulfide inclusion is acting as a nucleus for, or as a site for the nucleation of the voids. Both the sites we can see the voids are being formed around the manganese sulfide inclusion. And when we will see that the hard brittle particle is present at the boundary and it gets fractured, in that case also the voids will be formed somewhere, like iron carbide is present in this case, and its a fracture facilitates the formation of the voids and the gaps. So, there are three situations: a stringer type, that are sulfides and the other phases; a spheroidal type of the inclusions may be there of oxides and sulfides, and faceted particles in form of the nitrides. So, wherever the second phase particles are present, these will be acting as a site for nucleation of such voids, and subsequently their growth will be facilitating the dimple fracture. What we can see here, the inclusions are present, number of inclusions are present, and under the influence of the external load, the voids will be formed, and subsequently their growth will be leading to the subsequently their growth and coalescence will be leading to the generation of the fracture surface. So, this is one case where growth of incipient crack by enlargement and linkage of the voids takes place. But when these inclusions are present at the different locations, in that case there can be change in the direction of the fracture also. So, the slip band formation in the ligament between the voids also can take place. Say this is one location where void is being formed, and this is another location. So, in between the slip can occur and the shear fracture can be observed. So, this is the kind of thing can be seen in this fracture surface also, where continuous change in the direction of the fracture surface as per the presence of these inclusions and their void formation and their coalescence will be leading to the zigzag shape of the fracture surface. So, the location where these are present will also be affecting the kind of the way by which the fracture grows or the crack grows during the fracture. Now, I will summarize this presentation. In this presentation, basically I have talked about the role of the different factors in identification of the type of fracture, which includes the mechanical properties, macroscopic features, microscopic features, and the microstructural aspects also. And information about all these aspects will be helpful in determining the type of fracture in more effective manner. But in this presentation, primarily I have talked about the ductile fracture. Thank you for your attention.